Okay, today we meet for our 10th lecture on modern dynamical systems. And today's lecture is in a rather non-standard format because I'm going to give it online, but I hope it will be recorded and you will be able to find it. So today we plan to apply some algebraic tools that we developed at the previous lectures to pure dynamical plots. And the topic of the first part is called the recurrence of unipotent flows. Hopefully you already understand what the word recurrence means, but at the same time, it's the first moment when we define unipotent flows. So it's a good moment to do that. We fix UT as a one-parameter subgroup of SLDR. My favorite group for these several weeks. So we will say that it's unipotent if its derivative is nilpotent. What does it mean? It means that there exists a D times D nilpotent matrix. Such that for any T, our UT is an exponent of Tx. So our main goal for today is the following lecture, the following theorem, say not for today, but the first half of the lecture today, is the following nice observation. Theorem by Dani. It's an Indian mathematician, and Margulis. It's a Soviet American mathematician, a Fields medalist. So we fix UT to be a unipotent one-parameter subgroup of SLDR. And we take a point that belongs to the factor of SLDR or SLDZ. Then we claim the following thing, that for any positive epsilon, there exists a compact set K of SLDR factor SLDZ, such that for any positive T, one has the following inequality that we look at the subset when we go back to this K and we measure it, and it's big enough. So morally, it means that we go very often back to the compact set. And there is a really qualitative characteristics. What does it mean to go very often? Here, this thing means just a Lebesgue measure. On R, simply. So before we will discuss the proof, and as usual, I would like to restrict myself in the part when I'm supposed to prove something to two-dimensional case, just to illustrate some ideas, not to provide the full accurate proof. However, before I will prove, I will make a remark. Namely, you may suspect that the statement is rather trivial. Indeed, why can you think so? Because you may consider the following construction. Say we put a probability measure on the factor space, so it's SLDR invariant probability measure. of the space SLDR vector SLDZ. And you may consider a sequence of a compact subset inside of this set, such that their measure goes to 1 when n goes to infinity. Sets inside SLDR, SLDZ. And we assume that this sequence of measures goes to 1. So then we know that the action of our unipotent one parameter subgroup on the SLDR factor SLDZ is mixing. And in particular, it means that it's ergodic. The action of that's what we checked previous time, but for example, when we studied this Hovey-Moore theorem, so it's ergodic. Then we can apply Birkhoff ergodic theorem. And say that for mu almost always x SLDR SLDZ, and for any n, we have the following, that the average of these values of t, such that we went back to Kn, goes when n goes to infinity to mu of Kn. So obviously the statement that we made in our theorem holds for mu almost any x, because this thing is even more accurate in some sense. So there is an impression that we easily get a much stronger statement. But this impression is wrong. And the reason is exactly the same as what we discussed at our previous lecture dedicated to Hovey-Moore. Namely, it's easy to see that the theorem holds for mu almost any x. So the theorem holds for mu almost any x in SLDR vector SLDZ. But if you are attentive, you already notice it, that here I stated it for any x. We want it to be true for any x. And as we discussed previous time, this is the key difference between the homogeneous dynamics and ergodic theory. Ergodic theory is a very powerful thing, but basically there is no way to state anything that would hold always. All the theorems you may imagine, they hold almost always, at most. While in homogeneous dynamics, we can replace almost any by any. That's what we want to do. So one more remark before we prove the theorem. We can consider the example. And the example is the following. I want to illustrate that it's important that I chose the unipotent one parameter subgroup here, that it's not just because, for instance, it's more convenient to prove. It's a crucial thing. So unipotent condition is crucial. In order to illustrate it, I will show you an example. We consider d just equal to 2. So x will be SL to Z. And as a one parameter group, we will consider our favorite one that you already saw when we were studying the geodesic flow. Hope you remember it. So it's a one parameter group. And then we will consider the factor SL2R, factor SL2Z. And you can easily see that if I denote it by AT, then ATX can go to infinity when T goes to infinity. You can see it directly, but I will also explain it once again, because while we will be proving the theorem, we will need some more tools. So at the moment, you may just believe me or use the linear algebra to check it. Later, I will show you that it's a result of general thing. So then what does it mean? It means that then this guy contains non-zero vector whose norm is A minus T. And then it means that, unfortunately, if we remove the statement about unipotency of the one parameter subgroup, our statement will be simply wrong. So now I'm ready to prove our theory. In the case of D equal to 2, let us consider the unipotent subgroup of the group SL2R. And it's easy to see that all of them are conjugated. It follows, for instance, from the existence of a Jordan decomposition. So they all are conjugated. Thus, we can assume for any T that in reality our UT is nothing else but a Jordan self. So it will be this matrix. Now we will consider GZ2. G is somebody in SL2R. And we will consider an element X who is G SL2Z. Then this guy is a unimodular lattice in R2. And we have to distinguish two cases. Case number one corresponds to the situation when this set contains a non-zero vector in the x coordinate axis. So it contains non-zero vector in the coordinate axis R1. So there is just a guy who has only first coordinate and it lives in our set lambda. So let us consider the intersection and choose V as a generator of this set. This set is non-empty, so we can generate it with some vector. And then we can consider a complement to this vector in R2, so it's a basis in our lambda. So in particular, that means that the second component of W is not zero, otherwise they will be parallel to each other. This we don't want, so we can continue. And in this case, we can say that for any T, UT of W is W1 plus T W2, W2. But we know that W2 is not zero, so we can take T0 equal to U1 divided on W2, 2, and consider UT0 of W. It will give us W plus V. So we know that UT0 of lambda is lambda itself, that it's invariant. So point X does not move if it's a member of this set. And so the orbit of X under UT is compact, and then the result naturally follows. Now, what happens if we don't have such a cool vector that would be just a member of the coordinate axis and at the same time the member of lambda? So let's do it. Sorry. Case number 2. They do not intersect. Now we want to prove a lemma that will help us to check that the trajectory of UTX spends most of its time in the compact subsets. So before we state the lemma, I want to introduce one important notion. It's the notion of system. So if we take whatever lattice, not necessarily this one that we deal with in this lecture. So if it's a lattice in RD, I can consider a system to be a norm of the smallest norm of non-zero vectors from this lattice. So the lemma is the following. I will denote it by star because, as you remember, I told you that we will use it to check how things work in our counterexample. So it's the moment when you will see that it's the same thing. So we choose a subset of SLDR vector SLDZ. And E is relatively compact if and only if there exists a positive epsilon such that for any X, G, S, L, D, Z in E, the system can be separated from 0 by epsilon. So let me prove this statement. First, we assume that E is a relatively compact set. So it will be that direction, to the right. Let L be a compact subset of SLDR such that E lives inside of LSLDZ. It exists because E is relatively compact and because E is a subset of these factors, so we can multiply by elements of E and get element of SLDR. Now we set C to be a supremum of G minus 1. We take the norm when G is a member of L. Then for any non-zero V in the D and G in L, one has GV greater or equal than 1 over C. Now the opposite direction, conversely. In this case, we want to show that E is relatively compact when we have this condition about the system. So we assume that there exists such an epsilon as in the statement of the corollary. And for positive T, we set A epsilon T equal to A11 will be greater than epsilon, and for others, they will satisfy this condition. Maybe I want it to be strict, not so important. E plus 1, or E between D minus 1 and 1. So it is the same as to say that we fix that it lives in AT and A11 is greater than epsilon. AT was defined at the previous lecture, but if you don't remember the definition, don't worry, we provided it here. So now we will use what we did at the previous lecture. And moreover, at that part, even 2 lectures ago, at the part when we were discussing why SLDZ is necessarily a lattice inside of SLDR, you remember we constructed a representation KAN, and then we were choosing some parameters, and that's what we will use now. And we will follow a similar logic. So we claim that E can be incorporated outside of K, A with the chosen parameter 2 over square root of 3, and with the chosen parameter 1/2 SLDZ. So how to check it? You remember that SLDZ is a lattice in SLDR. So how did we prove it? We chose a smartly set STU such that we could generate it like that. It was a way how we proved that SLDZ is a lattice. And this STU was constructed as K, AT, and U. And then for any G that lives in our SLDR, we can represent it as a composition of K, when K lives in this big group K, A, when A lives in our A marked with 2 over square root of 3, and N, when N lives in N 1/2. So we could write it like that, and then we have to add here to SLDZ. So we have to write gamma, where gamma is a member of SLDZ. So in particular, what can we say about it? We can measure the norm of such a vector, and it will be exactly A11, because you multiply gamma minus 1, so you only deal with this K, AT, and U, and then you multiply E1, so you take the first coordinate, so it's A11. So if we know that G SLDZ belongs to E, and then we have no doubts that our A belongs to A epsilon 2 over square root of 3. And now we claim that this guy is a compact subset of A. This is our claim. We don't know it a priori. So it's time to check that. Why it should be true? Indeed, if we take any A in A epsilon T, then for all I between 1 and D, all integer I, of course, AII should be greater than T minus A11 minus I, sorry. It follows from the condition we put on the diagonal elements of A. So, but we know that this person would be estimated by epsilon, so we can say that we have here epsilon instead. So we also know that ADD is 1 over A11, etc., A D minus 1, D minus 1. So A1 II can be estimated in the following way. T D minus I, A11, A D minus 1, D minus 1. And this we can estimate from above, saying that it's D plus 1 minus I, epsilon 1 minus D, because each A can be estimated like that. So you just need to sum up all the T's and get what you have for epsilon. And then you can see that all these coordinate functions, they are bounded on A epsilon T. So we know that A epsilon T is compact. Oh, sorry. Now we need to show that the systole is not too small. The systole of this to show that the systole of the lattice ut lambda is not too small. So we set E as it's a systole, so we consider such a set. And what do we want to know about this set? First, we make one more notation. We say that phi t is a part of this lambda. It's a set of vectors such that their norm coincide with the system. So it's those which we establish this minimum. And then for any v, which is not 0, but lives in our lattice, we denote by EV the set of T in E, such that V enters this FT. So EV, it should be both open and closed. I will explain why in a second, in E. But therefore, we will see that for any T in AV, our FT is just V itself, maybe multiplied minus 1. So we need to explain why it's true that it should be open and closed first, and then we need to explain this last statement. So about open and closed, we look at AV. We say that it's formed by those T, such that for any W that are not zeros, the norm UTW is greater than this one, okay, greater or equal. And so obviously it should be closed. Now, why it should be open? Because we can take T that lives there, and we can consider a neighborhood of this T. Such that USD is smaller than 1/2, where S lives in this neighborhood. So if S lives there, then we claim that Fs should be plus minus V. Because if we take any S with this property, and we take any other V prime that lives in Fs, what do we have? We have that the norm of this thing it does not exceed this norm because that was a requirement. We had to achieve the level of systole, and this was smaller than 1/2. So we know that if we consider the determinant of the matrix that is formed by these two vectors, it should be smaller than 1/4. If you want, it's a Cauchy-Bunyakovsky inequality. But we also know that our lattice is unimodular. So necessarily this determinant should be an integer. But if it's an integer, then it should be 0. But if it should be 0, then they should be linearly dependent. And since it's unimodular, the only way is when they coincide up to the sign. So now we can consider the set of connected components of E. And we know that this set is at most countable. We cannot have uncountable number of connected components, so it's at most countable. Then we can take a member of this set, and by the property we discussed above, there exists a vector V that lives in our lattice such that for any t from this connected component, the systole is reached exactly at level V. And by assumption, we know that the assumption of our case 2, the moment where we can use it is that we know that that is not parallel to our base vector. So then we can be sure that if we multiply it on ut, we will go to infinity in its norm. Because you remember we fixed ut to be a Jordan cell. So we know that we multiply by t, something which is non-zero, it will not vanish, so it will go to infinity when t goes to infinity. And therefore, we know that I is a bounded interval. Good. Now we can see that by construction, AVI by its norm is exactly 1/2 multiplied by minimum of S and N1. So we take epsilon between 0 and 1/4 of this quantity. And we study the set of t in I such that SUT lambda is smaller or equal than epsilon. Let's try to compute. What do we have in this case? So we can take W, which is URVI, that our T is A plus R, and it belongs to I, and SUT lambda does not exceed epsilon. So W1 plus RW2 squared plus W2 squared. That's exactly what we have as a norm of URW. And it cannot exceed epsilon squared. If our W2 is bigger than epsilon, greater than epsilon, sorry, then we have a problem. We have no solution for this inequality. So we have to assume that it's not. And then, so let's say otherwise. That W1 squared, it's 1/4 of this minimum minus W2 squared. So it's greater or equal than the same thing minus epsilon squared, because we said otherwise. So this should be not smaller than the corresponding minimum, because we put some condition on our epsilon. And therefore, for t greater than a, the set a UTV is greater, smaller or equal than epsilon is empty if t is smaller than the corresponding thing. Otherwise, what do we have? We can look at the set of elements such that the corresponding norm is smaller than epsilon. And we can estimate it in terms of W2 and its norm. But we know what happens with this norm. So we can write the following formula. And summarizing, we had different opportunities, but in any case, for any positive t, we have this set with the condition that the system is smaller or equal than epsilon. And the Lebesgue measure of this set can be estimated as follows. Intersection of the interval 0t with our AB. AB, they are borders of connected components. So it means that if you look at the set that we were thinking about, so this set SUT and epsilon, and you look at its Lebesgue measure, then you can say that you may compute it by summing up on all the connected components. SUT is smaller than epsilon, and each of them you can estimate and say that you have this guy, and under the sign of sum, you will only preserve this part. And you sum up over all connected components. So this you can estimate. And the only thing that we are missing is exactly the statement of our lemma. You remember we said that we have a lemma where it is, it's this one. So we said that if we can estimate this system, the minimum of this system, then we have a relatively compact set. So we need only to apply this lemma and we are done. This is the end of the proof of the Horler theorem. In case when d is not equal to 2, you may follow a similar logic, but you will need to do much more work. In particular, you need to run the induction, which is called Besikovich induction, and it will be the induction exactly on the dimension of your group. I suggest you to skip it. It's enough for me if you understand the general idea, but if you are interested, you may follow the original paper by Danish to figure out how the argument looks like. And now we arrive to the top of our crash course on homogeneous dynamics to the main result that we will be interested in. I'm not going to prove it at all. I will just explain you the statements, and at the next lecture, we will see how to apply it. But it seems to be the most efficient and the most beautiful part of the homogeneous dynamics as it is up to now. And it's called Ratner's theorems. There are results by Marina Ratner, very important mathematician who was a student of Yakov Sinai and who completely changed the face of the homogeneous dynamics and gave in particular Margulis very impressive tools that allowed him to prove Oppenheim conjecture, the problem that was famous in number theory for many, many years and stated unsolvable. And another reason why I'm so excited about the Ratner's theorems, because they gave a basis for a future work of Maria Mirzakhani and Alex Eskin, who proved later a very important and beautiful result in Teichmüller dynamics. So my plan is to explain you what Ratner's theorems are about today. And on the next lecture, Kirill Zernikov will give a talk, and then we will see how to apply Ratner's theorems to Oppenheim conjecture. And if we have enough time, I will at least state and explain what it is, the theorem by Mirzakhani and Alex Eskin. So let us look at the theorems. As before, we live in the homogeneous space. By homogeneous space, informally, I just mean that this space looks the same when viewed from any point of that space. So the sphere is an homogeneous space where the cube is not. But more formally, we prefer to think about it in terms of the actions, as you saw. So we want to have a space plus an action. So it's action of group of symmetries, which is a transitive. Transitivity here means that if you are given 2 points x and y, and they both live in our space, then there should be G, one of the symmetries, such that we can obtain 1 point from another one by the G action. So it's not hard to see that in this case, your X always can be identified as a set with action of G with a quotient G gamma, it's some subgroup of G. How to find this gamma to see X as such a quotient? You can think that you take a point and you consider its stabilizer. So G gamma, there is G gamma X, but we know that gamma are done in a way that if you multiply it, you get the same. So it means that you have Gx. As an example, let's take again our favorite homogeneous space S2, and we can act there by SO3. So it's an example. And we will have the identification of SO3 vector SO2. And in a similar way, we can take our another favorite space, the hyperbolic plane, and see it. We already talked about it in our previous lectures when we were studying geodesics. So there is a way to think about many different spaces as about homogeneous spaces. So maybe I should say a few words because my Apple Pencil that wants to eat a little bit. So we will only consider now very special homogeneous spaces, namely those whose symmetry group is connected finitely dimensional Lie group. In particular, up to now, we were always thinking about SLD, but R or Z. But in general, in homogeneous dynamics, people work a lot with Lie groups and do not restrict themselves so much. So we want our X to be a finite volume space. In particular, any compact homogeneous space has finite volume, but the opposite is not true. And there is a very natural example of a non-compact homogeneous space, which is a modular curve. That's what we studied when we were discussing the geodesic flow and checked that it's in a continued fraction. So you can see it as a factor of SL to R on SL to Z, and then additional factor on SO to R. That's what you get in the modular curve, and you have cusps, and so there is no compactness. Now you can take a U, which is a subgroup of G, and U acts on X, UX, GX, G is in U, it's an orbit. If U is not normal, orbits can be quite different. Because, okay, for normal subgroup, it's hard to get anything non-trivial. In particular, what you can see is that they can be closed subsets. Can be closed subsets of X. But it's not always true. So the example is very standard one. You may think about two-dimensional torus. So it's a two-dimensional torus. And then you consider some non-rational direction, and as you take X alpha X, so it's a line, if you want, or windy. And I hope you already learned from all the previous things we discussed that it will be a dense one-dimensional subset, but it's not closed. So at the same time, what can you see from this example? That it's not closed. But if you consider a closure, then you get something cool. It's very nice. So you can see it as a Hx for some intermediate group H. So it's an orbit of some intermediate group. And what would be cool is to have such a classification of orbits in some abstract framework, not only for tori. Unfortunately, if you take whatever flow, it's simply not true. I mean, it's not true that you always have a similar property. And the most standard example that you may think about is the ones that we studied so long in this course. Namely, you have to take the geodesic flow on the surface of negative curvature. So you can consider the action of the group ET00 E minus T. It will be your U when T is real. And this group is isomorphic to R itself. And then you know that sometimes this flow is quite chaotic. And in general, the existence of the exponential part causes instability. So what could be the best hope people may have in this context is to eliminate the exponential part, kind of eliminate all exponential behavior and try to prove something nice for those who are not exponential in any sense. To say something nice exactly means that the orbit of any subgroup, they are either closed or dense in a larger closed orbit. Larger means that you take a larger subgroup. So that's what we would like to try to do here. And that's our best plan. So we first need to explain what does it mean that we eliminate any exponential part. So we consider a one-dimensional matrix group U gives you AT, T is an R. So, and we want from A to be a matrix with logarithm. So AT is exponent of T of log A. Typically, coefficients of AT may contain some exponential part. But if we require a little bit more from A, namely, we can say that we want that A is a unipotent matrix. So to be unipotent as before just means that you take an identity and sum up with some nilpotent matrix. As in our context of Dany-Margulis theorem. So in that case, AT is simply polynomial in T. So maybe it will be enough to get rid from this exponential part that makes our life so chaotic and unpredictable. You may put it in a more general framework, saying that you take G, which is an element of a Lie group, and it's nilpotent if it's a joint action x to gx g minus 1 on the Lie algebra. G is unipotent. But if you never heard about joint actions, you just ignore this part and you think about the model I gave you in a pure algebraic language of linear algebra. So we are ready to state actually Ratner's theorems. And the first one is the Ratner's orbit closure theorem. So we take homogeneous space of finite volume with connected finitely dimensionally group as a symmetry group. U is a connected subgroup of G generated by unipotent elements and UX is an orbit of element X. Then the closure of UX is an homogeneous space of finite volume. In particular, this means that there exists a closed subgroup H, which is in between U and G, such that the closure of Ux is exactly Hx. This theorem is Raghunathan conjecture. And literally it asserts that the orbit of any unipotent flow is dense in some homogeneous space of finite volume. In some applications, density is even not enough, as you know. We always may want more from the point of view of ergodic properties. And sometimes we need not the density, but equidistribution. And apparently, great Ratner has the answer for us, even in this context. Let me do it in a second. So, Ratner's equidistribution theory. So we take everybody as before, X, G, U, little point X, and H. They are all as in previous theory. And assume also that U is a one-parameter subgroup. For some homomorphism GT. Then we claim that its orbit is equidistributed in Hx. So it's not just dense there. In Hx. What does it mean to be equidistributed? For any continuous function, f from Hx to R, we may consider the integral, then normalize it, take a limb, and then it's just the same as to integrate f on the normalized R measure on Hx. So this result was conjectured by Dani, the person who proved the previous theorems that we discussed with Margulis. And it's a very efficient tool to study the ergodic properties of the group actions in homogeneous spaces. And so the last theorem is the one that gives us the classification of possible invariant measures that we may have for such an action. So it's the third and the last one. It's Ratner's measure classification theorem. As usual, we have a finite volume homogeneous space for a connected Lie group G. We have U, which is connected subgroup of G, generated by unipotent elements. And we have a measure. And this measure is probability measure. On X, which is ergodic under the action of U. Then we claim that mu is simply a Haar measure for some Hx. Some closed, finite volume, orbit Hx for some H. Sorry, it's not zero, it's U. So we know everything about the measures. If we have some ergodic measures, then it's a Haar measure and nothing else. So we know everything about the closure if we live in this cool unipotent world. And we know everything about the measure as well. These theorems were really magic at their time. And still it makes a very strong impression on me, the fact that we can get so much information, so precise classification. And I will show you how to apply them next time. If you're interested in proofs and examples, I strongly recommend you a book by Dave Morris dedicated to Ratner's theorems. And since today's lecture is in a rather non-standard format, I suggest us to stop here.